On this video, we're going to talk about the extrema on an interval. This is standard C1. This starts on page 90, so go ahead and put that in your new table of contents that you got today in class. So we talked about the idea of a max and min today in class. We reviewed stuff that we learned in Algebra 1 and then again in Algebra 2. So we're going to determine absolute and relative extrema, so absolute and relative maxes and mins, using the derivative process to determine the characteristic of a function. So that's kind of the purpose of today's video. So a couple of definitions. When we talk about extrema, we're talking about the idea of a max or a min. Okay, so that's just kind of the plural for max and mins. We call them extrema. So that's just a max or a min. Okay. So we define a minimum. Remember, a minimum and a maximum are a y value. So we say that f of c, so a certain y value, is a minimum on the function in a given interval if it is less than or equal to all of the other y values in its interval, in the area. Okay, and then a maximum is kind of opposite of that. It's the y value that's greater than or equal to all of the other y values within a given interval. So when it comes to extrema, there's two types. There's what we call the absolute, sometimes it's called a global, and one we call the relative, and that's called a local as well. Okay, an absolute extrema, or an absolute max or a min, is a max min that is the absolute highest in all of the function, in all of the interval. So there is no other y value that is part of it within any given interval. When we talk about absolutes, that interval has to be a closed interval. So go ahead and get that down. Relative are the max and mins that you guys are used to studying, that you studied in Algebra 2 and pre-cal when you talked about max and mins of any type of polynomial function. And those can occur on a closed or an open interval. What we mean by closed and open interval. So an open interval is usually a function that goes from negative infinity to positive infinity, where a closed interval is a function that has a definite start and a definite stop. Okay, so if we look at our picture here, and I'm going to expand it just a little bit, not mark it up, but expand it. There we go. Okay, so now I'm just moving stuff around. So if we think of this graph, and we think about the points A, B, C, D, and E, we can define them as maxes and mins first. So A we would consider to be a min because it's a low point. B we would consider to be a max because it's a high point. C a min. D would be a max. E would be a min. And F would be a max because it's a high point for its area. Now this is a closed interval because it starts at A and ends at B, so it's only between those values. So we are talking about a closed interval. Okay. Now because it is closed, we can have what we call the absolute max and min. We only have one absolute max and one absolute min. So we look on our graph to see which is the highest most point. And on this graph, that would be B. So that's going to be our absolute max, A for absolute. If we look at our lowest point, that looks to be A on our graph. So that represents the absolute min. That means that every other max and min are relative. They're only maxes and mins for the area that they're in. So for instance, D is a max because for the area, the points directly to the left and the points directly to the right. It is a high point. Okay, so every kind of max and min you guys have studied to this point has been considered to be a relative, with the exception of our parabola. That actually has an absolute minimum or an absolute maximum because of the weight shape. But the rest of the polynomials do not. Okay. So let's look at a couple of graphs. If we look at A, I can definitely see that we have an absolute highest point and an absolute lowest point. So for A, I would say my absolute, AB, for abbreviation, max is of course the y value, so that's going to be that point right there. So 1, 2, 3, 4, and 5. So a max of 5. And it's going to occur at x equals 2. we definitely have an absolute min, that point right there. So absolute min of 1, our y value, at x equals 0. So definitely we have an absolute max and an absolute min, but if we look at this interval, this is a closed interval from -1 to 2. Okay, so it includes -1 and it includes 2. Now for b, we do not have an absolute max because where the absolute max would be is an undefined value. So no absolute max, but that absolute min still occurs. Still the same one. So it's still 1 at x equals 0. Okay. On C, we definitely have that absolute max, same one as the first graph, of 5 at x equals 2. But where our min would be is undefined. So we have no absolute min. And the reason we don't is because on B, this is not a closed interval. The interval is actually -1 to 2, but it's open on 2. And then C is not continuous on the interval. It is a closed interval, but it's not continuous on that entire interval. So the only time we have an absolute max and an absolute min are if two things are true. If we have a closed interval, 1, and 2, if it is continuous. And that's the essence of our extreme value theorem, one of the big theorems in calculus. The extreme value theorem just says that if we have a function that is closed, has a start and a stop, and is continuous along every point within that interval, that we are guaranteed absolute max and an absolute min. We have both. So two things have to happen in order for this to be true. One, the function has to be continuous. And 2 has to be closed. So the function has to be continuous and it has to be closed. That just means it has to have a start and a stop, and every point in between that start and that stop has to exist. Okay. Now we can find these absolute maxes and absolute mins, and maxes and mins in general, by looking at what we call the critical value. Remember, x is where this is occurring, y is what it is. So the first step in figuring out a maximum and a minimum is to figure out your critical value. And a critical value is any time that our derivative right here is equal to 0 or it is not differentiable, which means something is going on in the function. If that's the case, we have what we call a critical value. And the next theorem says that critical values, or relative extrema, so maxes and mins, occur only at these critical values. So if I can find the critical value, I can determine the max or min. Well, that's an easy process for us because it involves the derivative, and like we talked today in class, that maxes and mins have a slope equal to 0 at that point, which means we can use our derivative equal to 0 to figure out where this is occurring. So for example, if I wanted to find the critical values of the function x cubed plus 3x squared minus 9x plus 2, the first thing I would do is take the derivative. Okay. Basic polynomial function, a cubic function. The next thing I would do is set it equal to 0 and start to solve. But like with most polynomial functions, the way we solve them is in fact to use factoring. So that's exactly what I'm going to do here. First, we have a GCF of 3, so I'm going to take that out. And then that makes it a little bit easier to factor. So x plus 3 and x minus 1. So that means x is -3 and x is equal to 1. So I have critical values, CVs, at x is equal to -3 and 1. So I have two critical values, which makes sense because of the fact that most of our polynomial functions, this one in particular is a cubic, is going to come up, go down, and go back up again. So we have a max and a min, which means we have two critical values. This is not necessarily the graph of this function, just an example of a cubic. So the second one, we can find critical values, again, first by finding the derivative. So this is a shortcut that I'm going to use. Remember, the derivative of u produces u prime over 2 square roots of u. So I'm going to use that property. So I get my u is this. That's my u. So 2 square roots of u. And then, of course, derivative on top. I could simplify that. I get x over the square root of x squared minus 4. Okay. So this one's a little bit different because we're dealing with a rational equation. So equaling 0, remember we take our numerator, equals 0. Okay, and for undefined, our denominator equals 0. Okay. Because critical values are not only where our function is equal to 0, but where it's also defined, we need to be able to find that, or not differentiable. Most students do not know what the graph of the square root of x squared minus 4 looks like, so you wouldn't see this part, but the graph actually looks like this. It looks like that. So we definitely have a max and two minimums. Both of those points are not differentiable because they are cusps, but our derivative process actually allows us to find them because of the fact that we have a fraction as a derivative. So the first thing I'm going to do is take my numerator and set it equal to 0, and then take my denominator and set it equal to 0. So the first one is already solved for me, so I have a critical value at x equals 0. I'm going to put that one down. And then solving the next one, the first thing I would do is square both sides. 0 squared is just 0, and that's quadratic, so I can factor it. I get that. So that means x is equal to -2 and x is equal to 2, which means my other critical values are -2 and 2. Okay, so the first step to determining maxes and mins, and absolute maxes and mins, are in fact to get the critical value, because if we have a max or min, it can occur at the critical value. With absolutes, there are 3 places that it can occur. Interior, inside the graph, at a critical value like this, or at the endpoints. So we're going to look at a problem like that. If we want to find extrema, so maxes and min on a closed interval, the fact that we say closed interval, that automatically means that we're talking about absolutes. Okay. And we identify absolutes by using what we call the candidate test. We first have to find the possible candidates and then figure out what the y values for each of those candidates are. So we want to find our derivative to find our critical numbers, and then we want to evaluate each of those critical numbers in the function, and as well as the endpoints. So critical values and endpoints are candidates, are possibilities for maxes and mins. Okay, so we want to look at all of those points to determine which one is a true max or a min. Because just like from the graph that we started with at the beginning, our absolute min occurred at an endpoint, but our absolute max occurred within. It wasn't necessarily an endpoint. So that point right there and that point right there. Okay, so what we want to do there is now look at a problem where we have to do that. So It says find the absolute maximum and minimums of f on the given closed interval and state where these values occur. So, looking at my endpoints, those are two of my candidates. Okay, my other candidates come from my derivative. So I want to take the derivative of this equation. So 6x minus 24. Okay, set it equal to 0 to get my critical value, and I can factor this. Even though it's linear, we can still factor, which means x is equal to 4. Now the question I want to ask at this point is, in fact, does that critical value fall in the interval we're looking? If the answer is yes, then it's a candidate. If the answer is no, we would just ignore it and just use our endpoints. So if I want to find which one of these values is the absolute max and absolute min, I need to plug them in. So I'm going to use a t-chart for that. So the x's that are the candidates, we have the endpoints -1 and 5, and then we have the possible candidate of critical value of 4. We're going to plug it into the main function, so I'm just going to write that there. This is the equation I'm plugging into to calculate the actual y value, because that's what tells me my max and min. So all I'm going to do is plug in. And I'm just using that middle space for work. So we get 3 plus 24, which is 27, minus 1, which gives us 26. So when x is -1, my y value is 26. If I plug in a 5, we're going to do the same thing. So 5 squared gives us 25. 25 times 3 gives us 75. So that right there is 75. 24 times 5 gives us minus 120 minus 1. So negative 45 minus 1, so negative 46. I might be a little off there. And then the last one. We want to plug it in because what we're looking for is our highest value, our highest y value, and our lowest y value. Okay. So 4 squared gives us 16. 16 times 3 gives us 48. You might want to leave yourself a little room to do some scratch work or do some scratch work on the side. 16, so 96 minus 1. So 48 minus 96 gives us negative 48. Negative 48 minus 1 gives us negative 49, which means I have an absolute max of 26 at x equals -1, because that's my highest y value, and an absolute min of negative 49 at x equals 4, since that's my lowest y value. So my highest y value occurred at the endpoint, but my lowest y value actually occurred within the interval. So what I want you to do is to try B and come in with a solution tomorrow. If you have any questions, come see me in the morning.